Swayam Prabha. Digital India. Educated India.
Namaskar. So, in the last class we discussed about the basics of Norton's theorem and we did some the examples with the help of the sources which were independent in those circuits. Now, in today's class we continue our discussion on Norton's theorem, but in this class we will discuss more about the cases where we have dependent sources available in the circuit. So, let us see the Norton's theorem which we discussed in the last class. Let us recap the Norton's theorem which we discussed in last class, which states that the linear two terminal circuit can be replaced by an equivalent circuit consisting of a current source I n in parallel with resistor R n, where I n is the short circuit current through the terminals and R n is the input or equivalent resistance at the terminals when independent sources are turned off. Independent sources turned off means the voltage source would be short circuited and the current source would be open circuited. So, finally, we will get the Norton's equivalent as shown in this figure, where I n is nothing but the short circuit current which is flowing through the terminal A B, and the R n is the input resistance which you will see when you see the circuit and you see through these two terminals the input resistance. The value of that would be nothing but Norton's resistance. So, what the independent or the unknown variables in this case are R n and I n, and this is we have to find out. Now, R n can be found in the same way we found R T H, that was the Thevenin resistance which we did in the Thevenin theorem discussion, and for the Norton's equivalent current I n, what we have to do? We have to short circuit the current flowing from terminal A to B. So, in the network, suppose this is your network and you have terminal A B like this, you have to simply short circuit and find out the value of what is the short circuit current. So, this network would be linear two terminal, because you want to short circuit these two terminal and find out the value of short circuit current. So, that short circuit current would be nothing but the Norton's current. Now, in the last class we discussed two cases, rather we discussed first case in detail, and we mentioned that there are two cases are available there for finding out the Norton's resistance. So, now in case 1 in the last class we discussed, if the network has no dependent source, then what we have to do? We have to turn off all the independent sources, and in that case R n would be the input resistance of the network looking between the terminals A and B. So, as we saw in the previous figure, so when you look through the terminal, suppose if these are the two terminals and you want to find out the Norton's resistance, then you have to look through these two terminal, and the resistance which you will see from these two terminals would be Norton's resistance. So, now this was the case which we discussed in the last class. In today's class we will discuss more about case 2, that means if the network has dependent sources. So, in that case what we have to do? We have to turn off all the independent sources only. That means that we will only turn off the independent sources while we leave the dependent sources connected to the circuit. So, in that case, as with the Thevenin's theorem, we discussed previously, the dependent sources cannot be turned off as they are controlled by the circuit variables. Since we have the dependency in the case of dependent sources, we cannot remove them from the circuit, and we analyze the circuit for Norton's equivalent by keeping the dependent sources connected to the circuit. Now, how to solve it? We have to apply voltage V naught at the terminals A B and determine the current I naught, and R n is also found in the same way as we analyzed the Thevenin's equivalent and found the value of R T H, that is Thevenin resistance. Now, what we have to do to find R n? We have to first set the independent voltage sources equal to 0. So, suppose if you have the network like this, where you have two terminals A B. Now, what you have to do to find the value of R n? You have to connect a voltage source V naught across terminal A B. So, you will connect one voltage source that is equal to maybe 1 volt or maybe any specified value. Why we keep 1 volt? Because it is easier to, it simplifies the calculation for finding out the value of R n. So, it is not mandatory that you always keep V is equal to 1 volt, you can take any value and solve the circuit. We take as 1 volt because it is easier. Now, you can see that we have Norton's resistance as V naught upon I naught. When we have V naught is equal to 1, it is simply the reciprocal of the current which is flowing through the terminal. So, this would be I naught and this is anyway you have the V naught. So, if you have V naught as equal to 1 volt, so R n would be simply the reciprocal of the current which is flowing through the terminal A. So, using these equations, you can easily find out the value of Norton's resistance. Now, next is we need to find out the value of Norton's current. That means, you have to short circuit the terminals A and B. So, you have the network, you have the terminals A B. Now, you need to find out the value of short circuit current. That means, you have to first short circuit both of the terminals and find out the value of current flowing through short circuited terminal A B. So, for this what you have to do? You have to just apply either KVL or KCL, whatever is appropriate for that circuit, and find the value of short circuit current. So, this short circuit current will be nothing but the Norton's current, and the final circuit which you will get would be the current source, that is I n, and in parallel with you will have the Norton's resistance R n, and that is A B. So, you will simply replace the unknown, that is linear two terminal network, with the Norton's equivalent. So, how we will do? Let us take one example so that we can understand this concept clearly. Suppose the circuit is as we see in the figure, and we need to find out the Norton's equivalent. If you see the circuit, you will see that there is one dependent current source and one independent voltage source. The dependent current source I x, the value of that current source is 2 I x. I x is depending upon the current which is flowing through the 4 ohm resistance. Now, what we have to do to find out the Norton's resistance? We have to first set the independent sources equal to 0, but leave the dependent sources as it is in the circuit. So, that means what we are doing? we are simply removing means you are short circuiting the voltage source and leaving the current source as it is. So, what will happen? Now, the voltage source is short circuited, you are leaving current source as it is in the network because it is a dependent current source, and then you have 5 ohm resistance which is there in the circuit in parallel with dependent current source. 4 ohm resistance you see is now short circuited because the voltage source which was available here, we short circuited that voltage source. Now, to find out the value of R n, what we have to do? We have to apply a external voltage supply V naught, that is equal to 1 volt, and find out the value of I naught which is flowing through this external voltage source. Now, if you see this circuit, this segment of the circuit, what is there? You will see this is the short circuit component because of the voltage source we short circuited. So, the 4 ohm resistance which you see here is now short circuited. So, what happens when you short circuit resistance, that means that the current flowing through resistance will be 0 because this will have the least resistance and whole current will pass through the short circuit wire. That means that the value of I x would be equal to 0. Now, what we are seeing here, since I x is equal to 0, that means this current source, that is 2 I x, will also be equal to 0. Now, what happens when I x is equal to 0? You have this component 0, the current which is flowing from external voltage supply V naught would be only through the 5 ohm resistance. So, what we get, the current I naught is nothing but 1 volt divided by 5 ohm resistance. So, when you calculate I naught, you get as 0.2 ampere, and the Norton's resistance you can simply calculate, that is V naught upon I naught, and that is nothing but 5 ohm. Now, if you see directly from this figure, if you do not apply voltage supply here, then also you can make out the Thevenin's the Norton's resistance. Why? How you can get it? Because this is anyway short circuited. So, this component is out, this is 0 now because the I x value is 0. So, you are left with only this 5 ohm resistance, and which would be finally your input resistance when you see from terminal A B. So, you can straight away say that the Norton's resistance would be 5 ohm. So, you can just cross verify that what you have got from V naught upon I naught is nothing but 5 ohm, which you can find out through inspection also. Now, the next task is how to find out the value of I n, that means the short circuit current across the short circuited flowing through the short circuited terminal A B. So, what we have to do? We have to just short circuit the terminals A B. Now, we have assumed that there is a short circuit current I s c, which is nothing but the Norton's current, and you have the circuit. You need to find out the value of short circuit current flowing through short circuited terminal A B. Now, if you see the figure, that 4 ohm resistor is in parallel with 10 volt voltage source, and 4 ohm resistor is also parallel with dependent current source. So, that means if you see this particular segment A and B is short circuited. So, finally, what you are getting here is nothing but the voltage source in parallel with another 5 ohm resistance, because this will be in parallel, and then you will have dependent current source of 2 Ix. So, this you get when you do the inspection of the circuit. And where is your terminal AB? Terminal AB would be here. Okay. So, now this is a simplified circuit which you will get from here. When you see this, what you get? You get the value of current Ix which is flowing through the 4 ohm resistance. The 4 ohm resistance value, the current flowing through 4 ohm resistance is, because you see this voltage V which is across the node 1 and node 2 is nothing but voltage applied across 4 ohm resistance also. So, we with the help of this updated circuit you can easily find out the value of Ix is nothing but 10, that is the value of the voltage source 10 V divided by 4 ohm resistance. So, now you get the value of Ix. When you get the value of Ix, you have to just run the KCL at node and find out the value of the short circuit current. So, if you see here, the value of short circuit current is given by first 10 divided by 5, because if you see this figure, this is again in parallel with 10 volt. So, you get 2 ampere as a current, that is 10 by 5 plus 2 times Ix, right. So, if you see this and this is coming here, and this is what value? This is short circuit current, because it is between A, B. So, if you see current flowing between A, B, that is Isc, is nothing but current flowing through resistor 5 ohm as well as current flowing through the dependent current source. So, now Isc is nothing but 10 divided by 5 plus 2 Ix. So, if you put the value of Ix which you just calculated, you get the value of Isc is nothing but 7 ampere. So, now this 7 ampere is your Norton's current and 5 ohm is the Norton's resistance which you calculated. So, with this way you can find out the Norton's equivalent of the circuit which was given in the example. Now, let us see another case which is different from our previous example. In this case, we need to find out the Norton's equivalent, but the important thing which we see here, that this circuit does not have any independent voltage or current source. So, what will happen in that case? So, when you short circuit the rightmost terminal, that is if you short circuit them, current would be 0. Why? Because there is no any other source available in the circuit which can supply current I. So, if it is open circuited, like in this case, the current I would be 0. Even if it is short circuited, current would still be 0, because the source which can supply this current is not available in the circuit, and this dependent voltage source which we see here depends upon the value of current I. So, what you can say, that you always have open circuit voltage 0, short circuit current also 0. So, it means that you need not to find out the value of Norton's current, because you cannot find out Norton's current as we see there is no any independent voltage or current source. So, next what we need to do, we need to just find out the value of Norton's resistance. So, what we will do, since we do not have any independent source, the value of VOC and ISC is 0. So, to find out the value of Norton's resistance, we just place 1 ampere source externally and measure the voltage across terminal. So, let us say the voltage across terminal is V test and we apply 1 ampere current source across these two terminals and find out the value of V test. Now, the value of Rn, that is Norton's resistance, would be value of V test divided by 1 ampere, that is the equivalent resistance which you will see, that is simply the input resistance which you see from these two terminal. Now, if you see the figure, what you can observe, that the value I is nothing but minus of 1 ampere, because both are in opposite direction. So, current I would be minus 1 ampere. Now, if you apply nodal analysis here, what you can write, since V test is across these two terminals. So, you can see V test across the 2 ohm resistance. Now, what you need to do, you have to just apply Kirchhoff current law at this node and find out the value of V test. So, at this node you will first see V test minus 1.5 into I is minus 1 ampere. So, this will become 1.5 into minus 1 divided by 3. So, that is current flowing in this direction. So, let us say it is I dash. So, I dash is nothing but V test minus of the value of this dependent voltage source divided by 3 ohm resistance. Now, the value which is flowing through this would be V test divided by 2, and then when you apply Kirchhoff current law, it means that the sum of these two would be the value of current flowing inside the node. So, what is the value which is flowing inside the node? That is 1 ampere. So, when you see this particular equation, you have only variable which is V test. So, you can easily solve this equation and you get the value of V test as 0.6 volt. So, you get the value of V test as 0.6 volt, you divide it by 1 ampere current, which is the current source we applied, we get the value of Rn, that is Norton's resistance, as 6 ohm. So, the Norton's equivalent of the circuit which is given in the example would be simply 0.6 ohm without any current source. So, that means In will be 0 in this case. So, now let us summarize what we discussed in case of Thevenin and Norton's equivalent. To determine the Thevenin or Norton's equivalent, the circuit can be divided into two networks. As we see, you have two sections of the circuit. You can say this section is network A, and where you see the load or the resistance which is of your interest to find out the value of either voltage or current, that would be separated from the main circuit, and it is called as network B. So, you can divide the whole circuit into two parts, one is network A, another is network B. So, what next is that network A is simplified to evaluate either Thevenin or Norton's equivalent. So, you will see terminal AB here. The left of this would be having either Thevenin or Norton's equivalent, so that you can solve it by adding that equivalent to the resistance, or that is the network B, and find out the circuit variables across RL. So, what we do in case of Thevenin's theorem? So, given any linear circuit, we rearrange it in the form of two networks A and B connected by two wires. Network A is the network to be simplified and B will be left untouched. So, in this circuit, this would be simplified and this would be untouched. Then if there are dependent sources, its controlling variable must be in the same network. That means, if there is a dependent source in the circuit, the variable should also be in the same circuit. So, both should be inside the network A for analysis. Now, disconnect the network B, define a voltage V open circuit across the terminal of network A. So, that means we will apply VOC across these two terminal and turn off or zero out the every independent source in the network A. Then what will happen? We will form an inactive network, but we have to leave the dependent sources unchanged. So, what we will get from this? We will get input resistance across the terminals of network A, and when we get the input resistance, we again put all the independent sources back. That means, when we found the input resistance of the circuit, we simply short circuited the voltage source and open circuited the current source. So, we will again put the independent sources back to the circuit, and then we will find the voltage, that is open circuit voltage across the terminal of network A. Opposite to the Thevenin's, we have the Norton's theorem, because in this case, instead of open circuit voltage, we need to find out the short circuit current. So, here also, given any linear circuit, you have to rearrange it in the form of two networks, that is A and B, which are connected by two wires. Network A is the network to be simplified and B will be left untouched, as in the case of Thevenin's theorem. In this case also, the dependent sources and its controlling variable must be in the same network. Now, we disconnect the network B, define current ISC, that is the short circuit current. So, you will short circuit these two terminals, right, and you find out the value of short circuit current flowing through the shorted terminal of network A. Turn off or zero out the every independent source in the network to form an inactive network, while keeping the dependent sources in the network. Now, again we have to find the input resistance. So, if you see Thevenin's and Norton's theorem, the input resistance is same in both of the cases. The only change is the short circuit current, which we need to find out in case of Norton's equivalent, while in case of Thevenin we need to find out the open circuit voltage. So, here if you see the the equivalent of Thevenin equivalent, this would be VOC is nothing but VTH in series with resistance RTH. So, this would be Thevenin's equivalent, while in case of Norton's you will have current, that is short circuit current, or you can say it is Norton's current, and then in parallel you will have resistance Rn, that is Norton's resistance, which will be which would be found similar to what we did analysis for RTH. So, in both of the cases finding out the resistance will be same. Change would be in case of finding out either the short circuit current or open circuit voltage. So, with this we close our today's session. So, in this session we found we analyzed the Norton's equivalent when the dependent sources were available. So, in next class we start with another theorem which is which is very important from circuit analysis perspective. Thank you.